today we have our first video for Chapter 3. Chapter 3 is all about solving systems of equations. So first off, we need to say, what is a system of equations? Well, this coming directly from your vocab, system of equations is a set of equations with the same variables. So we can have 2 equations, 3, 4, doesn't matter how many equations we have, but they all have to have the same variables, like they all have x and y, or they all have z and l, or something like that. So in our first example here, we can see that we have a system of 2 equations, one being 2x plus y equals 5, one being x minus y equals 1. Now what does it mean to solve a system of equations? Well, essentially that means we want to find the one spot, or possibly more spots, usually just one, where both of these equations have the same x and the same y value. If we look at like our bottom one, x minus y equals 1. Well, if I set x to be 3, y has to be 2. That's the only y value it can be. If x is 3, y has to be 2. Well, that might not necessarily be true in our other equation. If x is 3, it looks like y would have to be negative 1 to make that true. So there's really only going to be one spot in most cases where we'd have the same x and y in both equations. Now there's a couple different ways to solve our systems. Today we're going to look mainly just at graphing them. So anytime you want to graph a system of equations, it's best to put them into slope-intercept form. That's the easiest way to graph them, so you just change each one individually. So for our first one, I'm going to walk you through the steps of how to change it to slope-intercept form, but a lot of that is something we did last chapter, so after this example, I'm just going to write the steps on there and not necessarily walk you through it all. So in our first one, if we have 2x plus y equals 5, well, in this case, I would subtract 2x from both sides. When I do that, we would get y equals negative 2x plus 5. And that is already in slope-intercept form, so we're actually done. So I'm going to move that up here and say that was our only step. We did minus 2x from both sides. Now, for our other one, if we have x minus y equals 1, same thing. We need to get it into a y equals mx plus b form, so it's easier to graph. Well, the first thing I would do is subtract x from both sides, just so we're getting only y left on our left side there. So we'd have a negative y equals negative x plus 1, because we had this minus y here, so it's going to be a negative y. Okay, now we have negative y equals negative x plus 1, but we want positive y. So to make sure we can switch our signs here, we're going to multiply both sides by negative 1. Multiply over here by negative 1 as well. When we multiply everything by negative 1, it basically just switches all the signs. So that negative y becomes positive y. The negative x becomes positive x. That plus 1, or adding on a positive 1, becomes adding on a negative 1. So our right side becomes x minus 1. So our steps in that case, second one was times negative 1 and minus x. So subtract x, then times negative 1, and that's how we got our 2 slope-intercept equations. Now that they're slope-intercept, it's a lot easier to graph them. So we can look first at our top equation. Used to look like 2x plus y equals 5. We switched it around, and now we have y equals negative 2x plus 5. It's a lot easier to graph because it has that plus 5 as our y-intercept. So we're right here. Our slope is negative 2, so we go down 2 over 1, down 2 over 1, down 2 over 1. Makes it a lot easier to see where they got this line from. So after we plot a couple points, we'll say that's our line there. Same thing with our second equation. We'll do this one in green. Now that it's a slope-intercept form, we can say our y-intercept is at negative 1. So we start right there. Our slope in this case is going to be 1, because it's just 1x. That means we go up 1 over 1, up 1 over 1, up 1 over 1, and so on. So again, it's a lot easier to see our lines now. Now they labeled them over here in their original terms, so x minus y equals 1 and 2x plus y equals 5. But we know that those mean the same thing as our slope-intercept forms. Now that we have graphed our lines, we just look and see, well, where do they intersect? They seem to intersect at 2, 1. So in this case, we'd say that's our solution, 2, 1. And it makes sense, because if we go back to our original equations, plugging in 2 for x and 1 for y, we'd say 2 times 2 is 4, plus 1 equals 5. So this one is indeed true. Same thing, 2 minus 1 is 1, so this one is also true. So that's the only point, 2, 1, where both of these equations would be true. That's the solution to our system. Now, different systems can be classified as different things. So when we're looking at graphs of systems of linear equations, they may appear to be intersecting lines, they could be parallel lines, or they could even be the same exact line. If we worked with those equations and we got them into slope-intercept form, and they actually came out to be the same exact line, that is a possibility. Now, when we just have our intersecting lines, like our far left one here, you can see there's only one spot where they intersect each other. So we say there's only one solution. If they were two lines, so I had one right here, I'm going to do the other one in blue, I graphed my other one and, oh, it's right on top of that red one. Technically, every single point on that line is a solution, because both lines go through all of those points. So in that case, we would say there's infinitely many solutions. There's an infinite number of points that would be on both of those lines, because they're the same exact line. And if we're looking at parallel lines, there's no spot where they'll ever intersect. There's no spot where this line is the same as this line. So we'd have no solution to that system. Now, a system of equations is called consistent if it has at least one solution, and then it would be inconsistent. I want that. There we go. It would be inconsistent if it has no solutions. So the only way to be inconsistent is if you have the parallel lines. A consistent system would be called independent if it has exactly one solution, so that's our intersecting lines. It would be called dependent if it has an infinite number of solutions. So you can see that right here, consistent and independent is just the one point. Consistent and dependent is when it's all of the points, because it's two lines on top of each other. And just simply inconsistent is our parallel lines. In our next video, we'll look at a couple different examples.